Hey guys, today I brought you this guy. This is Niklas Rosenstein, and he is one of the most talented Python devs that I know personally.
Thanks.
And he brought quite an interesting project with him, so tell us about it.
Yes, I was looking for a project to learn a bit more about Houdini, and I came across a dataset called Gaia, Gaia satellite data, and it contains over 1 billion objects in space. They're coordinates and a lot of a broad spectrum of recorded measurements about these objects from different senses.
So it's like a cartography project for space?
Yeah, that's actually the ultimate goal. Okay. And there's a smaller version of the dataset because 1 billion points in Houdini, for example, is quite a lot. So we're going to start with a little bit less. And there's a smaller version containing only 2.5 million objects. Okay. And these are actually stars. They verified that they are stars and improve their accuracy with previous data. And I'm going to show how you can download this data, import it into Houdini using Python. And then we're using Vex to convert this data to visualize it in Houdini.
So we're kind of building a star map today.
Yeah, we're going to build a star cloud.
Oh, that sounds very intriguing because I finally decided that now the moment has come that I cannot get around Python any further. So I'm really looking forward for this. And I guess let's get started.
Yeah, let's go. Hello and welcome to my tutorial on Entagma. I'm Niklas Rosenstein. Today I want to show you how you can import CSV data into Houdini. I was looking for datasets to import into Houdini. I came across the Gaia archive, which is hosted by the ESA, the European Space Agency. They provide information or data from their satellite that they launched in 2013. And you can find that data if you go here to the ESA archive. I'm gonna add the link to the description and go to the downloads page. And then you're in some kind of FTP directory. And there's the Gaia source and the TJS source, and I'm going to explain what these are in a bit. There's also some documentation about this data, so let's look at that first. Here we can see something about the Gaia source and the TJS source. Actually, the description or the columns in this data is about the same for both of them. The Gaia source is actually the full data set that they released. So it contains about 1 billion objects in space, not necessarily stars, because it also captures other objects illuminated by stars. And the TJS source is a smaller data set that is compared with other previous data sets from the Hipparcos and Tycho 2 mission, as they mention here. It contains only 2.5 million stars. And these are actually stars, so they verified that these are actually stars and not any other kind of objects. The columns are pretty much the same. There's a few more, a few less. Looking through these, we can find that there is available a longitude and latitude. So these are spherical coordinates that we can use to calculate XYZ coordinates in the Houdini viewport, or the Cartesian coordinate system of Houdini. There's also something called PHOT G mean mag, which stands for photometry G band mean magnitude. After looking through some articles online, searching, Googling, I found out that this is actually a different representation of brightness, of star brightness, which is called magnitude in astronomy. If we look through this Wikipedia article, we can find that there's some formulas, and we're going to use that formula later to calculate the actual star intensity or its brightness. At the top, there's also the parallax. And the parallax is basically the angle or the apparent movement of the object behind its background when you're looking at it from two different positions. So there's an article about that as well. I'm going to link that in the description. That describes how parallax works, how it's measured for stars. And there's also a very simple formula to calculate the distance of the star using its parallax, which is just 1 divided by the parallax. However, we later have to make sure that we're actually working with arc seconds, because otherwise the formula is not correct. You have to take the units into consideration correctly. If we look again in the archive, we can find that there's CSV data, FITS data, and vote table data. Now these are some astronomy file formats. We're going to work with the CSV format because it's the easiest to parse into Python. And if you look at the Gaia source CSV directory, you can find that there's about 5,000 files in there. Yeah, so this is a lot of files, and this actually amounts to about 200 gigabytes of compressed data. And this is a bit unintuitive to work with, especially if we're just experimenting and starting out with loading the data into Houdini. Once we're done loading data into Houdini and verify that everything works, we can easily switch to using more data. But for this tutorial, we're going to use the TJS source, which consists of only 16 parts, making up 600 megabytes in compressed data. Now, for these 16 files, it's pretty easy to download them by hand. But once you want to download the full Gaia dataset, it's going to take a while for you to click 5,000 and download 5,000 files. So we're going to write a small Python script to download these files. But first of all, we need to install Python. So we're going to do that now. go to python.org, go to the downloads and choose Python 3.6.1 or Python 2.7.1.3. Houdini actually comes with Python 2.7 and Python 2 is currently still the standard in the VFX industry. However, that's going to change soon. So if you go to pythonclock.org, you can see that Python 2 will be deprecated in 2 years and 8 months. And that's when also the VFX industry has to decide to switch to Python 3 at least. So Python 3 is a bit more modern, but if you're just starting out with Python, it's probably easier to start with the Python 2.7 because you won't be confused when you're working with Python outside of Windows and inside Houdini. So we're going to download that and click. Run that. Make sure you install for all users because that's going to land on your main hard drive. You can choose to install it in program files instead of the main drive. These are all fine except for the Python exe should be added to the path so we can use it from the command line without any further ado. So we're going to choose to install that as well. Now that we have Python installed, we should check if it worked. So right click on the Windows icon and choose the Windows PowerShell. Now if you enter Python, you should see the interactive command prompt. Now, before we start writing our script to download the TJS files, we want to install a library called requests, which helps us downloading files from the internet. It's a bit simpler than using the standard library, so we need to install it with pip. And we can use pip install requests. However, pip does not come pre-installed with Python 2. So we need to Google for a script called getpip, which we can now save onto our desktop. Since we installed Python into the programs folder, we can simply check this by looking at the path to the executable. We need admin privileges, and we don't have them with the shell that we just opened. So let's open the PowerShell in admin mode. So let's go to our desktop, because as you will notice, we didn't start in our home directory. Sorry, this is actually... And now we can run the script with Python. What you saw there was tab completion. So I pressed tab and completed the file name for me. That's why I didn't write the whole file name. That's about it. If you now enter pip, it should work. And we also need to install the requests library from the admin shell. So let's do pip install requests. And I've previously installed it already, so it doesn't do it again. But for you, you should see that it's downloading the library and installing it. All right, let's go back to our normal shell. Go to our desktop. And here we will start writing our download script. So I'll open Notepad++, and then I'm quickly just going to save this as download py. We will need to use the request library that we just installed and also the OS module as we're doing some file system operations. Now, if you look at the TJS, let's search for Gaia archive again. Now download. TJS source CSV, you can see that these have all have very similar names, so we only have to replace or use the correct index here when to generate a new URL. I'm simply copying the address of the link, and I'm going to insert this as a template. So I'm using a raw string here, which wouldn't actually be necessary in this case. I just want to make sure that any kind of special characters, like backslashes, for example, if they would appear in the string, they wouldn't have any special meaning. I'm going to replace this last sequence of 3 zeros with a placeholder that I call index. And later we are going to replace the placeholder with the correct index, of course. We need to tell Python to make sure that the substitution string has exactly 3 characters and to fill the rest with zeros. So I'm going to add double colon 03D is the syntax for this kind of thing. You can look that up if you just search for Python string formatting. Now for our main function, we're going to iterate from 0 to 15. That's why I use xrange 16. And we render the URL using the format method. Saying index equals index, and just for testing purposes, we're going to print out the URLs that we generate. Now quickly call our main function when the script is executed from the command line. And let's run that from our shell. All right, that's looking pretty good. That's what we want. And now we can continue with determining the file name that the contents of the URL should be saved to. So we say file name equals, and we can use the POSIX path library which deals with paths in the POSIX file system. And since POSIX file system is based on forward slashes, we can also use this on URLs. So we can use POSIX path base name, which gives us this part of the URL. So then if this file already exists, because maybe you stopped the script at some point and want to restart it again, we can skip it. So if os path is file name, we can say print skipped file name and then skip the rest of the loop. Now we're going to use the requests library to open the URL, and it's very important that we stream it, because otherwise the contents of the response will be loaded into memory completely before we have a chance to work with the data. And, oh sorry, stream true, of course. And this way, if we stream it, we can read from the server. At the same time, we write the file to the file system. So that's a much more efficient way of downloading files. Now we open the file name in binary write mode, which is very important, because non-binary mode handles the content as text and will replace new line characters with the appropriate new line sequence for the platform, which in Windows case is CLRF, so character return line feed, which we don't want. So we just want to receive binary data and write binary data. Now we're going to iterate over chunks that we receive from the server. And the chunk size is 1024 bytes. And then we simply write that chunk to the file. And before we open the file or download it, I'm simply going to print that we're downloading it so that we know what we're dealing with in the console. Right, let's try that. Now this is going to take a while. We'll continue when the download is finished. You can see on our desktop all the files that we just downloaded here. Now these are gzip compressed CSV files. We could decompress them with 7-zip. So if I do extract here, we can look at it in Notepad++. You can see it's pretty huge. Yeah, we've got about 130,000 entries here. And this is the header, which says, which specifies the name of each of the columns. We do not want to decompress all these files because we can do that in Houdini from Python. And we don't really save time by decompressing them manually. If we do that from the Python script, it won't load much slower. So it's very convenient to load them directly from the compressed version. Now that we have the files, we can dive straight into Houdini. Let's start with a geometry node, and inside that delete the file node and create a Python sub. Now inside here, there's some default code, which we're not gonna delete because we need the node and the geometry that we're going to fill with the data. And you might wonder what the Who name is coming from. It's the Houdini Python module, which is available in this namespace by default. However, I find it confusing, especially for beginners, so I like importing it explicitly in the top of the script. We need a way to define in the node the directory where all our files reside. It's also convenient to add a parameter to limit the number of data points to load, because if we're only just testing our script, I'm searching for the string field. I'm blind at the moment. All right, there it is. And we'll also need an integer. Limiting the number of points to load to load with Python is very convenient when we're just developing our script, because loading the whole set is taking a lot of time, and waiting 2 minutes every time we change the line and to see if it works is not acceptable and doesn't make any fun. So I'm calling this one here directory. And actually I don't need a string field, but instead a file field that is read only. I'm going to call it directory. All right, let's apply that. Now here we can read our directory parameter. We can use the eval parm function, which will retrieve the parameter and evaluate it immediately. So we just get the value that you can also see inside here in Houdini. Now also do the same for the max rows. Just a little test. Let's do print directory and print max rows. Actually, we're in Python 2, so we don't need the parentheses. Oops. Let's run apply, and you can see that we have an empty string and 0. Let's go straight to our desktop where we have our TJS data files and press accept. Oh, sorry. Actually, for selecting a directory, you have to go to the parent directory, select the directory here and press accept. And now you can see that we have the path to the desktop for directory parameter. Well, we're going to need the CSV module because we're going to read CSV data, but before that we'll also need the gzip module to decompress the data on the fly. Now in our main function, we'll just check if we don't have a directory value. So if the string here is empty, we're just not doing anything. And also if the directory doesn't exist, we should also just skip the whole execution of the subnode. Now we'll need to figure out all the files that we want to load from the directory. So we're going to list the directory. So we say for name in OS list here directory, and check if the name ends with CSV gz. Oops. And we're going to add it to the files list. And we want to add that as an absolute path. So we join it with our previous directory name. And then we can sort the list because it kind of makes sense to load the first part of the data before like the second. So we're going to sort them by their name, which will automatically give us the right ordering due to how sorting strings works. And actually we also need to import the OS module because I'm using it here in this section. Now we can try printing the files list, and we also need to call our script, our main function. Set apply, and we see that we don't have a single file in there, and that is because I used CSV instead of CSV. Easy fix, and you can see that we have all 16 files in this list. Taking a look at our data, let's quickly reiterate what kind of data we want to extract from the CSV archive. We're going to decompress this again, one of these, and drag the file back into Notepad++ and check what data we need. We needed the parallax, which is right here. Note that it's all lowercase because in the documentation it was all uppercase, but actually all titles here are lowercase. And there, the very end, there's our LB and GFOD mean mag columns. Now we could kind of count what column indices the columns we want to have, but there's an easier way. We could just take every column name and associate it with the correct index, and then we can write the name of the column instead. I'll show you what I mean in a second. So we'll iterate over every file in the files list and open them with a gzip module, which will give us a file handle. From there we can read the uncompressed data, and we can wrap that in a CSV reader object. And just for test, we're going to read the first row from the CSV file and break right there, because we don't want to do this for every file for now. We just want to see the results for one file. I hit apply, and now the console, I suppose. Oh, I actually need to print the header, of course, that we see what's happening. And you can see here that we have a list of all of the header names. Instead of remembering the index of every of these columns or figuring them out by hand, we can simply turn this into a dictionary, mapping the name of the column to its index. So we say for every name in the header, we enumerate it, which yields us an index and a name. So that gives us like 0 for hip and like I think about 58 for the last one. Then we invert this and create a dictionary from it. Now print again. And we can see that we have a dictionary mapping, for example, the deck member or deck column to index 8. And now we can just use, for example, print header parallax. And that should give us index 10. And that means it's actually the 11th column in the CSV file, because, indexing starts from 0. Now we can start extracting the data from the columns that we need. Let's define here what columns we need. So I'm going to say this is an uppercase variable because it's kind of static information. So I'm saying we need the latitude. Sorry, the column name of the latitude is actually B. The name of the longitude is L. Then we also need the parallax and the FOD mean mag column. And I'm going to split this by the comma. This actually gives us just a list as if I was typing B, L, parallax, and so on. But it's a bit simpler. Now we need to think about how we store this information on the geometry. We could create a floating point attribute on the geometry for every one of these. However, points on the geometry already have like 3 floating point values, the X, Y, and Z coordinates. And since these are like not removable, the geometry needs these attributes, we can just reuse these members or these attributes instead of creating new ones and leaving the points set to 0. So we actually can store the latitude, longitude, and parallax in the point position and just create a new member for the FOD G mean mag column. So I'm going to say geo add attrib. It's going to be a point attribute with the name mag, and the default value is 0.0. If we were doing just 0, it will create a integer attribute because a 0 is just an integer, and if you pass it a float default value, it's going to create a float attribute. Now in here, we can go over every row in our CSV file and extract the data we need from this list of values. So I'm going to say b equals row. I'm going to retrieve the index of the B column. I'm going to do the same for the L column. Also going to do the same for the parallax. And for the magnitude. I'm really feeling uncomfortable with this editor. All right. Now, since these are all floating point values, we're going to use the float function to convert them because the CSV reader only gives us string values. And now we can create a new point on the geometry and set its position. And it expects a vector 3. And our vector 3 consists of B, L, and parallax. Then we can also set the attribute value of our mag attribute to the mag value that we just received. Now, before we execute this, or we could execute this now and we would read in only one file because of this break. Now, if you remove the break, it's going to read from all files. So first we should make sure that we're going to make use of the max rows. So we're going to keep track of the count, the number of points that we read in. And before checking a new file, we're checking if we actually already exceeded the number of rows to read. So if the number of max rows is greater than 0, because if we use 0, we should just read in everything, and the count is bigger or equal to max rows, we'll just break out the loop. And we're going to use the same here inside this loop. And after that, increment our count variable. Let's hit break. Now increment the count before continuing and hit apply. And I have a syntax error here. It's just because I missed adding the 1. And there's a small spelling error. All right, so something should have happened. If I use middle mouse button on the Python node, you can see that we have 1 point. Let's try to increase this a bit to 10. Still got 10 points. Let's check the geometry spreadsheet. And you can see here we have the values from our CSV file. Now that's basically it. I'll just set this to 0 here now to read in all the data, and I'll be back when it's done. Now we're back, and the load time was about 2 minutes. And you can see that we have a number of points in our viewport. Hit spacebar H, and you can see our points. And if you go closer, you can see that this already looks kind of like stars. This is actually like a world map, except for our nearby stars. If we open the scene again, we will have to wait the time to load all this data from the CSV files all over again. Now, instead of working on the output of the Python node directly, we can instead save it to a geometry file that I call, for example, tjsbgeo, and then read it in again with the file node. And there we go, with the same data. However, the cook time for this node was only 20 milliseconds, whereas the Python node took about 58 seconds. Now we can actually just get rid of our Python node and work completely on the data that we get from our file node. Now let's see how we can get these points converted into Cartesian space, because currently we're already in Cartesian space, but we have spherical coordinates represented in Cartesian space, and we have to convert these from spherical coordinates to Cartesian coordinates to actually get a proper 3D representation of our nearby stars. And to do that, we're just simply going to search for latitude, longitude to Cartesian. And the first result is pretty good. Now you might find different formulas online. It all depends on what axis you want to show where. Best way is probably to just experiment to get the right result. Like if this formula doesn't fit, check the next one. But for a star system, it doesn't actually matter that much. You know, like the relations between the distances and the positions of each star are going to be the same, just different, like maybe swapped or flipped horizontally or like vertically or along the z-axis. So let's create a attribute wrangle node. And here we can use this formula to create our coordinates. Like our radius is currently, we'll just set that to 1 for now because we didn't use the parallax yet. Now remember that our latitude and longitude values are in degrees. So we need to use the radians function to compute degree values to radians, because cosine and sine functions expect radians values. All right, let's bring this into vex syntax very quickly. And assign this to our point again, x, y, z. And let's see what happens. This is pretty bad. Check expecting semicolon, and I'm missing it here. All right, now you can see it's pretty small. Hit spacebar H again to center on the sphere because it's a unit sphere and our data previously was much bigger. Yeah, so if we go inside here, this is our Milky Way here, the thick band of stars, and outside of, that direction, there's less stars to look at. You can see there's some kind of, strips in this data. These are actually, you might think these are like we did something wrong, but actually these errors, they are real in the data set. If you look at the Gaia archive, in the visualizations page. And yeah, if I zoom in here, you can see the very same errors in this data, just as we do here. If you want to do like some nice renders, you should probably search some part here that is doesn't have these issues. Now let's calculate the star's brightness. The star's brightness is contained in the magnitude value. However, the magnitude is a very maybe counterintuitive value. So if you look at for Gmag, you can see that it's a magnitude. If you search for magnitude in astronomy, you can find this Wikipedia article, and here it describes, for example, how our sun has a magnitude of -27, whereas our moon, obviously being far less bright, having a magnitude of -13, so it actually has a higher magnitude value, although its brightness is lower. So magnitude is some kind of inverted brightness value. If we go a little bit down, we can find a formula that describes how to convert between magnitude and intensity. Here we have like M1 would be our current star's brightness, which we get from the TGS dataset. And then there's a reference magnitude value. And here we have our current star's intensity, which is what we're looking for. And here is the reference brightness. Now, the values we choose for the reference magnitude and intensity are kind of up to us because there's no real unit or value for, let's say, 100% brightness. There's only 0% brightness, but there's no fixed second value that we could use to say, okay, so this is 100% bright and our sun is like 5,000% bright or something. No, it doesn't work like that, because brightness is also based on distance, and we really need to choose these values so we get the kind of look we want in our viewport. This formula looks pretty complicated. You could solve it by hand for the I1 variable. Now, you could solve this by hand, but there's tools like, for example, Wolfram Alpha, that allow you to let the computer do the work. So we can simply type this expression or this formula into Wolfram Alpha and tell it to solve for a specific variable. We only need to use some simpler variables. So I'm going to use a minus b equals -2.5 log 10 of x over y instead. And I'm going to tell it to solve for x because that's our I1. I'm saying solve for x, double colon, and I'm saying a minus b equals -2.5 times logarithm to the base 10 of x over y. Let's hit enter. And here is our formula. We can type this formula directly into Houdini. So I'm going to say our mref be about like -1.5, which was, as Wikipedia said, the apparent brightness of Sirius, our nearest star that we can see from the night sky. Our iref, which is the intensity that this star appears to us. So the Sirius star with a brightness of 1.0. And I'm going to say our I1 equals iref, which is our y times exponential which is the same as something raised to the base of e, and 0.921034 times b minus the same value of times a. And now, actually, our a is our magnitude attribute, and b is our reference magnitude. Now we can simply set this brightness to our color and see what we get. Something is wrong here. Let's check quickly. Oh, I missed the @ sign. And yeah, so this is looking pretty dark. Let's add an mref member, which I actually already got here from a previous iteration. I just set its range from 0 to 10, and I'm going to use it here for the mref instead. Hit apply. You can see now this is looking a bit better. You know, we get some reasonable results at about like 7 or something. So basically what we're saying here is that a star with a magnitude of like 7 should get an intensity of 1.0, which is what we're saying here. And of course, stars with a higher magnitude will be lit a bit less bright, and stars with a lower magnitude will be brighter than that. And you can also see that if you check our geometry spreadsheet and sort by the highest color value. You can see, for example, the magnitude of this star is 4.3, which is lower than our reference magnitude, meaning that this star is brighter. We can see that by its color value, which has a color of 11 or intensity of 11, which of course we're not going to see that with our inner render. Yeah, now if you give this a quick rendering, let's hit render and see what's happening. Most likely all of our points are going to be a bit big. Yeah, so these points have a very high width. So let's change the width to something like 0.001 and let's do a semicolon, hit apply. All right, this is a bit too small maybe. Let's remove one of the zeros again. Okay, that's looking better. All right, now the magnitude value that we get is apparent. So it means this is the magnitude of the star as we can see it from Earth, or actually as the satellite sees it, I suppose. If we were to use some absolutely physically correct renderer and actual light sources for these stars and place them at their actual distance from our center, we would get incorrect results, because the actual brightness that we assign to each star is its apparent brightness, but its brightness will fall off over the distance to our center or from where we view it. So the correct way would be to use the absolute magnitude. And if we check Google for parent to absolute, this is actually wrong, parent to absolute magnitude, we can find this page, which gives us a formula to convert from apparent to absolute magnitude. We can basically use this to convert our mag value to an absolute magnitude and then plug it into the same formula to get the actual brightness of the star. So just to demonstrate how to do this, I'm going to say float mv, which is what they use for the absolute magnitude, equals our magnitude minus 2.5 times the logarithm, which is actually logarithm to base 10. So we actually need to use log 10 of the distance of the star. And let's just call this d for now, divided by 10. Actually, let's make sure that's float. And that is to the raised to the power of 2. So like this. And of course, d we don't have yet, so we still need to figure that one out. And for that, we're going to need the parallax. If we check for parallax measurement, you can find this page again. And yeah, as you might remember, the parallax and distance relationship is pretty easy. So the distance in parsecs is given by 1 divided of p, and p being the parallax measured in arcseconds. Now we have to remember that the parallax we get from the Gaia dataset is actually in milliarcseconds. So if we check the parallax documentation here, it says it's an angle in the unit MAS, and MAS stands for milliarcseconds. And it's basically the same as arcseconds, just divided by 1,000. Like a millimeter is 1,000th of a meter. So let's go back into Houdini and calculate the distance, which is, as we said earlier, 1 divided by the parallax, however, parallax in arcseconds. And to convert from our parallax in milliarcseconds to actual arcseconds, we can divide them by 1,000. Now, only thing left to do here is replacing our apparent magnitude with the absolute magnitude that we just calculated and press apply. Now, everything here is looking pretty bright. But well, yeah, as you can imagine, stars that are very far away must be very bright. Let's tone this down a bit. That's looking a bit better. Now that we have the absolute magnitude of our stars, actually, let's just go down to 0. We can also place them on their actual position in space. Since we have the distance, we can actually just plug this in for the radius. Press apply. And you can see that the stars are pretty far away. So, I can zoom out quite a lot. And this distance is in parsec, which is like 100 parsec are like 326 light years or so. Yeah, like this is not meters or kilometers, because obviously then the stars would be even further away and most likely exceed the number range if you were having 32 bits integers, which I'm not sure if Houdini is actually using. I'm pretty sure they're probably using 64 bits integers. This would render correctly if you were using actual light sources, with absolutely 100% physically correct renderer, because of the light fall off. These stars would appear as bright as with the apparent magnitude that we previously had, now because of their distance to us. Now to get a nice little star cloud, we can just divide the radius, the distance actually, by let's say 1000. Press apply, and you can see here that we have our star cloud. What might be irritating at first is that at the center we have some rather dark stars, and as we go outwards, actually all of them are pretty damn bright. If you think about it, it actually makes a lot of sense, because stars that are further away, their light is not going to reach us when they are rather dim. They must be very bright so that their telescope can actually capture them, and that's why as we go further away there's less stars and only very bright ones. Now since this is not, if you not that nicely renderable, we're going back to the apparent magnitude, up the reference magnitude back to 7 maybe only divide by 100, go back to the center, that's the render in the background here, try rendering that again maybe, render view, actually maximize Houdini again. Now, as you can see, stars are also closer to us than before when we calculated them on the unit sphere. Yeah, you might want to maybe change the size of the stars based on the distance, or use, actual light sources and try to find a way to make the light visible. Yeah, that's about it. Since I'm not the kind of render guy, I'm more into development. I'm not the one coming up with beautiful renders. That's your job. So I'm really looking forward to what you can do with this, and thanks for watching.